Hello, welcome to our presentation on HashiCorp Europe. We are representing the research lab of crypto and blockchain of Banco Santander. And we want to talk about the buzzword crypto agility, the problem that is behind this buzzword, and the solutions that people in the industry are seeking. We want to show you one specific example. So let's look at the agenda of the talk. First, explaining ourselves, why we're here, guys from a bank, talking about secret management technologies. We want to tackle the buzzword, the crypto agility, identify what really is the problem. And we want to look at a very specific example of this problem, very specific tiny instance that is tangible, and demonstrate how you can solve it using software like HashiCorp Vault. This is something we have done last year together with HashiCorp engineers. We created a couple of plugins. That was a great experience, but it's a portal to a new dimension of problems. So let's treat this as a little example or a little fragment of a whole new category of problems that we need to face. So first of all, why people from a bank are here talking about this? And the reason is that blockchain technology has been around for over 10 years now. Even the first iteration, software hacked away in a garage basically, has accumulated value, has sustained relentless attack in the open internet, and has sustained. So even not mentioning the market cap of things like Bitcoin and Ethereum that together are around $1 trillion, just the fact that you can actually use sort of internet as your ledger, if you combine cryptographic engineering with human engineering, if you incentivize properly, that is amazing. And this, of course, is not going to go unnoticed. So across over 10 years, people all over have been waking up to this new reality. Now you have both commercial and institutional banks experimenting with this technology. This technology seems to be there to stay, like the internet has proven not to be a fad. But now it brings for us a raft of problems that we need to tackle. And of course, where you have a problem, you have potential solutions. So what we observe is a new breed of software that tries to mitigate the gap. Now, Santander has been serious about blockchain technology. I should mention that in 2019, we have issued 20 million bond on Ethereum, that completely legal bond denominated in USD actually. Quite recently, we facilitated together with Goldman Sachs and Societe Generale an issuance to the tune of 100 million euro by the European Investment Bank. And you can imagine that this is just a tip of the iceberg. So if we can pull those things off, there is a lot of work under the surface that we possibly can't speak about, or it's just nothing showy, but there is a lot of work going on. So that's why we're here. Blockchain seems to be serious. Santander is serious about blockchain. Okay, so what's the problem then? And the problem is the mismatch between the creativity and open-mindedness of, let's call them CryptoPunks that created blockchain, and the noble conservatism of cybersecurity. So when you look at that, on one hand side, you have the crypto rebels, the originators of blockchain, that continue to innovate and continue to come up with new ideas. And they are using elliptic curve cryptography basically, but in most innovative ways. So they say, okay, let's use Schnorr signatures instead of ECDSA signatures. Okay, let's use the ECDSA signatures, but let us handle them differently. Or let us use multi-party computing. This is the flavor of the month in the crypto exchanges world. Or let us use zero-knowledge proofs so that the balances are not really exposed on chain. And then when you talk about those things to any real professional in cybersecurity, their reaction is going to be don't. Huh? Because their question would be, okay, but is it FIPS compliant? Huh? And is it happening in a secure place? What is the perimeter security? Just to get an idea, the process of cryptographic technology getting certified and approved and accepted is anything from 6 to 12 years. Looking at RSA, looking at ECDSA. And eventually, on top of that, the very distributed nature of blockchain is a bit of a nightmare or is a new challenge. Because blockchain by design, those technologies are to be spread across the globe, to be distributed, to be shared. While one of the pillars of cybersecurity is that I execute my cryptographic operations preferably in an HSM, which is like a steel box that nobody has access to, and if you try to X-ray, it explodes. So we have this mismatch. You need a glue. You need something to connect those worlds. And this is where new breed of software we identify is showing up. This is a big topic. The whole aspect of delivery across geographies, across locations, across clouds begs for a whole presentation of itself. Let us focus on a very specific problem of signing Ethereum transaction, though, so that we see a real problem and a real solution. So we see how software like HashiCorp Vault can actually help you solve problems that you have on hand. So let us look at the Ethereum transaction. And the Ethereum transaction is, or the Ethereum asset is like Bitcoin. Ethereum is controlled by a private key. And the shadow of the private key, the hash of the public key, is imprinted onto the asset. Now, when you want to manipulate the asset, you're sending a command that is called a transaction for some reason, and you sign it with a private key. But now it goes to the blockchain, and blockchain needs to verify the validity of the signature. And in the normal world, when we sign some PDF documents, some electronic documents, what we go to is a registry of public keys, and we verify if indeed the public key of somebody who claimed to have signed it creates the signature that is on the document. Now on blockchain, you don't have a public key registry. So the philosophy is different. What Ethereum does, what Bitcoin does, is it takes the transaction, it takes the signature, and tries to recreate the public key from the signature, which is almost possible. And from this public key, it recreates the address and compares with the address that is on the asset. So verification is pseudo-anonymous, and you go away without any public key registry. And it is very clever, and it does not work, at least not quite. And the reason is that some specific features of elliptic curve ECDSA signatures. So any elliptic curve signature is basically a riddle. And ECDSA just one, you have other like Schnorr signatures, BLS signatures are getting popular. Now, one specific thing about ECDSA signature is that the riddle that you play signature against is you use the hash of a document and the public key and the numbers from the signature to get a point on the elliptic curve. And you take the x-coordinate of this point. And you compare this x-coordinate to one of the original numbers. And if they match, if they are equal, you say, hey, the signature is correct, because coming up with a pair of numbers that would fit into this riddle and make it comply is next to impossible unless you know the private key. Alas, elliptic curves are symmetric. So there is not just one point with this x-coordinate. For x-coordinate of a specific value, small r, you have 2 points. So when you try to do elliptic curve ECDSA key recovery, you hit on ambiguity because you don't know which point you should use. You know, starting from x-coordinate, okay, so I can identify point capital R, and from this I can build my public key, and I'm good, but you don't know which of the 2 points R prime you should take. And you could do trial and error, but blockchain is kind of skimpy on computational resources. So instead, the originators of Bitcoin and by extension Ethereum came up with a different idea. They said, okay, to our signature of a transaction, let's add a flag that basically says, take the upper R or take the lower R. It's the third parameter. It's the parameter V that you can see on the slide. That's cute, but if you look at the standard signature, standard issue signature that you can get from an HSM, it's missing. It's a new thing. So HSMs cannot produce this for you, not yet, not all of them. Okay, the industry is playing catch up, of course, but your generic HSM can't give you this format of a transaction. So what happens now? Yeah, what happens now is that instead of HSMs, people use software to sign Ethereum transactions. And this means that private keys that control assets of potentially very high value are in memory, and because of distributed nature of blockchain, also possibly in many places. That's bad. That's very insecure, and that's actually happening. So what could we do about this? Well, in principle, as you may have seen from the equations, if you know the public key and if you have the signature, you are in position to calculate whether V should be up or down. So it's possible to take the HSM, generic, vanilla ECDSA signature, take the signer's public key, the message, and from this you can calculate your R, your capital R, the point on the elliptic curve, and you can verify if it's an up one or a down one, which allows you to calculate the V. So on the algorithmic side, this is not very complicated if you know a little bit about elliptic curves. Problem is where to execute such code. So what we really need is not only being smart enough to pull this trick off, but we need software that speaks to the HSMs to get us the vanilla signature in a secure way without private key leaving the HSM at any point. We need software that can collect the private key, the public keys, in a smooth, permissioned manner. We need software that can execute our little piece of code in a secure way. We need this software to allow us to operate on elliptic curve arithmetics, so it needs to have great support in terms of libraries. And of course, it all needs to be wrapped in a consistent system of permissions and policies. So if we had such software, and if we could embed our little piece of code in such software, this would be great, wouldn't it? Now, it turns out HashiCorp Vault fits the bill very nicely, and I will hand over to Pedro to give you some details about our little plugin that solves exactly the problem described. Thank you.
Hello everyone, my name is Pedro. I'm part of Siemion's research team, and now I will try to give you an overview of how our plugin looks on the inside. I will try to show you a couple of snippets of the code that we actually built inside HashiCorp Vault, and you will see that the process that Przemek has taught you before is not a complex process if you actually know what you're looking for and what you're doing. So first, let's get started by the beginning, which are the functionalities of our plugin. I mean, in this case, we have 4 functionalities, all of them permission, because all of them are only allowed for users. Each of the users has its own private key. For example, in the first functionality, that is creating a private key. When that user has already created a private key, he can actually access the address. That in Ethereum is something like an alias that you are shown on the network with. I mean, whenever someone wants to send funds to you or to contact with you through a smart contract, it needs to use your alias to know who is actually contacted to. The third thing that our plugin is able to do is to perform a signature in the standard ECDSA format. And the fourth thing is actually transforming this format to the Ethereum standard format. So let's get started. But first, let's talk about the external libraries that we are using. In this case, for the cryptography handling, we are using a couple of external libraries. The first one would be the Bitcoin library for ECDSA handling, for the arithmetics. And the second one would be the Ethereum library for handling the transactions, the hash, how the hash of the transaction is actually performed, and all those things. And in this part, we found pretty straightforward to implement it using HashiCorp Vault, because on other key management that we have used in the past, when you need to get an external library, you cannot import it like you would do in a normal code. You need to actually build it yourself. But with HashiCorp Vault, this part was just straightforward. So let's get started with the code. The first thing that you need to do when you want to actually perform the signing process is to gather all the information. In this case, as you can see, it's just getting the public key as an X and Y coordinate, and also the hash of the transaction. As you can also see, we are using the standard library from Go Ethereum to actually get the hash of the transaction, because we're wrapping up the transaction and we are getting the hash following the same algorithm. Once you have these two things, you only need to go, well, we can go for the next step. That is just, in this case, we have just done a mock-up of how an actual HSM would perform the signature. This could be also done with an external HSM, but in this case, we wanted to keep the whole lifecycle inside HashiCorp Vault, and we just perform the actual getting the key, signing the transaction, as you can see in the code, and then just converting it into an array of bytes. But this, as I'm saying, just to say it again, you can do it with an external HSM. Once you have this signature in the standard ECDSA format, you can go for the next step, which is actually, first of all, start extracting the RNS values from this signature. And once you have these RNS values, you just need to also calculate the inverse of S, because will be needed on the next and last step. That is where the actual magic happens, where we actually get this precious B value that Przemek has told us about. And this last step would be, as you can see, mainly is just performing the function that you see on the slide to calculate the R point. And in this case, when we have already this R point, you just need to go for the Y coordinate of the point and to get the first bit of it. And that is the value that we have been looking for. As you have seen, well, there are a couple of steps, but none of them is very complex. They are just some scalar multiplication and additions to get the expected R point. And just for double check, well, I wanted to include again the both signature formats, so you can see now that you have seen the whole process. You can now probably understand much better the actual difference between both of them, how the RNS values, which are in green and blue respectively in both of them, they are the same, and how we need to calculate actually the B value. And probably you have realized that the B value is not 0 or 1. That is what I have said in the previous slide. And this is just because the Ethereum team decided that they wanted it to be 27 or 28, respectively 2B and 2C in hex. There is just, it doesn't matter if they get 0 or 1, they just add up 27 from that value. And this would be the explanation of the actual plugin.
Okay, so what we have seen is an example of a glue code that finds its place in a framework that provides it permissioning, that provides policies, that provides proper deployment. And it actually solves one tiny problem between the blockchain world and the existing infrastructure. Of course, you may say this is just a stopgap, because HSM industry is catching up and those functionalities are getting onboarded. But the point here is that it's a never-ending story. And the creativity on the blockchain side is, I'd say, an order of magnitude greater than the appetite for catch-up game on the HSM industry. So we are gonna need this software, this kind of software, for a good while. Not to mention the aspect of distributing cryptographic services, which begs for another presentation. I hope you like this. You may Google the code. It's all tangible. It's all accessible. Thank you very much.